Okay, picture this, a future that's absolutely buzzing with AIs, all interacting with each other. We're talking self-driving cars, figuring out who goes first at a four-way stop. Our digital assistants juggling schedules, trading bots duking it out on the stock market. I mean, it's this incredibly complex digital dance happening all around us. But here's the big question, right? If every single one of those AIs is programmed to be, well, a little selfish, to just look out for its own best interest, how do we stop the whole system from grinding to a halt? How do we prevent total digital gridlock? So it turns out this isn't some brand new AI problem. It's actually a classic puzzle from game theory called a social dilemma. And it's the perfect way to frame this whole challenge, that constant tug of war between what's best for me versus what's best for us. And the most famous version of this has to be the prisoner's dilemma. The setup is super simple. You've probably heard it. Two partners in crime get busted. The cops put them in separate rooms. Now they each have a choice: cooperate with their partner by staying quiet, or defect and snitch on the other one. Okay, this little chart here, this payoff matrix, it lays it all out. Look, if you both cooperate, you both stay silent, you both get a pretty good reward. That's the best outcome for the team. But, and this is a big but, the temptation to defect is massive. Because if you defect while your partner stays quiet, you get the grand prize. But, and here's the kicker, if you both decide to defect, you both get a terrible outcome. And it's that mix of greed and fear that so often pushes everyone into that worst-case scenario. Now, for an AI, this is even trickier. There are two big reasons why. First, something called non-stationarity. Just think of it like this. The rules of the game are always changing because the other player is learning and adapting in real time. It's like trying to play chess against someone whose pieces can suddenly learn new moves. And second, there's equilibrium selection. Basically, there are a bunch of possible endgames, but most of them are, well, they're bad, like both players defecting over and over. So how does an AI even know which good outcome to aim for? All right, so the researchers looking at this problem came up with a really brilliant shift in thinking. They realized to solve this, you have to stop focusing on just playing the game itself, and you have to start playing the player. Yeah, this quote just hits the nail on the head. It's not about playing the game, it's about playing the other player's learning process. The whole point isn't just to make the best move in this single turn. No, the real goal is to make a move that actually shapes how your opponent learns, nudging their future strategy in a direction that helps you in the long run. And this really breaks down the two kinds of agents. On one hand, you've got your naive agents. They're purely reactive. They only look at the last thing that happened and decide what to do next. Super short-sighted, really easy to exploit. But then you have the learning-aware agents. Think of them as meta-agents. These guys are playing 4D chess. They're not just looking at the last move. They're watching how the other guy learns over hundreds, even thousands of games, and actively trying to guide that learning process. Okay, so the idea is awesome, right? But how do you actually get an AI to do that? Well, this is where the researchers rolled up their sleeves and built a brand new algorithm to make it happen. They came up with a new algorithm called Koala PG. And yes, that's a mouthful. It stands for Co-Agent Learning-Aware Policy Gradients, but the name tells you exactly what it does. And look, Koala PG is a pretty big deal for a few reasons. It's just way more practical than older methods. For one, it's provably unbiased. It doesn't get bogged down in ridiculously complex math. It's built for how AIs actually learn, in batches of experience. And this is the really cool part. It doesn't need to cheat and look at the other AI's code. It learns everything it needs just by watching what the other agent does, which is, how it would work in the real world. All right, but this is where the story gets really, really interesting and takes a totally unexpected turn. So we have this amazing, super smart, new kind of AI that can influence how other AIs learn. The next logical step seems pretty obvious, doesn't it? I mean, what happens when you put two of these super smart, learning-aware AIs in a game together? You've got two grandmasters, right? Both know the other is trying to shape them. You'd think they would just look at each other, realize cooperation is the smartest move for both of them, and just get on with it. Nope. That is not what happens. Not even close. In reality, when you pit two of these super agents against each other right out of the gate, they usually fail miserably. They get stuck defecting against each other over and over again, the exact thing they were supposed to prevent. It's because they're too smart, too busy trying to out-meta the other one, and they can never establish a stable pattern. So the researchers found this incredible, kind of counterintuitive path to cooperation. It's like a three-step dance. Step 1, the smart agent has to start by playing against a naive agent. Step 2, it learns how to basically extort that naive agent, teaching it through its actions that cooperation is the only winning move. And then, step 3, that skill it learned, the skill of forcing cooperation, paradoxically becomes the very foundation it needs to build real cooperation with another smart agent. It's wild. And that is the absolute mind-bending takeaway here. You can't just throw a bunch of super smart AIs together and hope for the best. It doesn't work. True cooperation needs diversity. It needs a mix of these far-sighted, clever agents and the simple, naive ones for the whole system to learn how to work together. So, okay, that's the theory. But what does this look like in a more complicated, more realistic world? Let's take a look at how this all played out in a much more complex game. All right, so they tested this in a simulation called Cleanup Light. Here's the deal. Agents can either harvest apples to get points for themselves, or they can spend time cleaning a polluted river. Cleaning the river means more apples grow for everyone later. It's that classic tragedy of the commons problem. And as you can see, the results were night and day. The Koala PG agents just blew the baseline methods out of the water, earning a way higher average reward. And this chart shows us why they did so much better. They actually learned to cooperate. They figured out how to divide up the cleaning work much more fairly. They also stopped using this aggressive zapping beam on each other nearly as much. So they didn't just rack up more points, they actually built a better, more productive, and less aggressive little society. And this quote from the paper itself just puts a perfect bow on the whole thing. The presence of short-sighted agents turns out to be essential for full cooperation to be established among far-sighted, learning-aware agents. The naive agents aren't a bug, they're a feature. They are literally the training wheels that teach the smart agents how to ride the bike of cooperation. So, what's the big takeaway from all this? Why does it matter? Well, it suggests that when we're building these huge AI systems, maybe the goal shouldn't be to make every single agent a hyper-rational, perfect genius. Maybe the real secret is to create a diverse digital ecosystem, a place where different kinds of AIs, smart and simple, can all learn from each other. And that leaves us with one final pretty deep question to think about. This research, it's about more than just code and algorithms, isn't it? It's about the very nature of how cooperation begins. So as we continue to build these societies of AI, we really have to ask, are we just engineering intelligence? Or are we engineering the very conditions for digital trust?